Hello everyone, this is Prasan. Welcome to our first ML project. In this video, we are going to talk about the iris dataset and its analysis using Python. This is a classification problem. So without wasting any time, let's go and see our dataset. This is our dataset. It contains three classes of 50 instances each, where each class refers to a type of iris plant. One class is linearly separable from the other two. The latter are not linearly separable from each other. Here is our attribute information. You can see sepal length centimeter, sepal width centimeter, petal length centimeter, petal width centimeter, and the species contribute our attributes. So let's go back to our notebook and start importing our libraries. The first one is the pandas. The pandas is going to help us in reading the dataset, while the numpy will be helping us in the operations for array. OS will be helping us to compile our notebook. Matplotlib and Seaborn are going to help us in visualizing data as graphs. So let's go and press Ctrl Enter in order to start our notebook. The next step will be loading our dataset. It can be done by using df equals pd dot read underscore csv, which is also known as comma separated values. As the dataset is in the same directory as our notebook, hence we will not go into the path but directly write iris.csv. In order to preview the first 5 rows and columns of our data, we will be writing df.head. So here is the preview of our data. So in the second step, we are going to delete a column. As you can see, the ID is the same as the first serial number, so we don't need it anymore. In order to delete the column, we will write df equals df.drop columns equals id, and then if we preview this, you can see the id has been deleted. Next up is displaying our stats about data. In order to do that, we will be writing df.describe. So here is our data. In order to display the number of samples on each class, we would be using df species.value underscore counts. What this will do is tell us about our species, that is Iris setosa, Iris virginica, Iris versicolor, and tell us about the number of these species. So now comes our main work. We will be doing the pre-processing. Firstly, we will be checking for null values in this data. So in order to check for null values, we would be writing df.isNull brackets dot sum brackets. Once we press enter, we will see that we don't have any null values in this dataset, so we are good to go. So now starts our exploratory data analysis, which is also known as EDA. So in order to do that, firstly we would be starting this by using histograms. So histograms will be used by the help of our matplotlib library, which we have imported earlier. So in order to use the histograms, we would be writing df brackets our attribute dot histogram columns. Once we type this, here is our first histogram. We would be doing the same thing for the other parts also. So as you can see, I have created histograms for each of our attributes. Now, what we are going to do is use a scatter plot in order to make this more presentable. In the scatter plot, we would be using colors, which would be red, orange, and blue. For the particular species, that would be Iris virginica, Iris versicolor, and Iris setosa. Next, we would be setting the range. So we would be setting our attributes as I in range 3. X would be our species, and we are going to use plt.scatterx sepal length centimeter and x sepal width centimeter, where C equals our colors and labels would be species. We have already mentioned the colors here and the species also. So next we would be using the simple function plt.xlabel in order to label the x-axis as sepal length and the y-axis as sepal width. Let's go and plot this. So here you can see a graph in which the x-axis is sepal length, y-axis is sepal width, and the colors represent our three species. Let's go on and do the same for the petal attribute. Here's the graph. Now what we will be doing is using the C-bond in order to get a cumulative graph. So in order to do that, we would be using sns.set underscore context, the notebook. This will help us in making the graph. Here we are terming the attributes as ax equals df dot plot dot hist, in which bins would be 25 and alpha would be 0.5. As you can see, bins is the number of bars which I have been using by the particular attribute, and the different colors have been used in order to visualize different attributes. So our next part is to create 4 separate plots using pandas.hist method. So it can be easily done by using axlist equals df.hist, in which bins again would be 25. Now we are going to add x and y labels to the first column and the last row. Once we do that, we can ignore this warning. And here you can see the cumulative graph, and here is the 4 separate plots of histograms of each attribute: sepal length centimeter, sepal width centimeter, petal length centimeter, and petal width centimeter. Next up is the box plot. Box plot is also a very essential visualizing technique which can be used to generate data. So we have used the species attribute in order to view our box plot. Similarly, we can also use pair plot. Here, this is our pair plot. As you can see, the species are mentioned by the color red for Iris setosa, orange for Iris versicolor, and green for Iris virginica. You can see the diagonals of all these tell us that the sepal length centimeter and in both height and width are usually the same. So this is a very important piece of information. Next up is the correlation matrix. So you must be wondering, what is a correlation matrix? A correlation matrix is a table showing correlation coefficients between variables. Each cell in this table shows the correlation between two variables. The value is in the range of -1 to 1. So if two variables have high correlation, we can neglect one variable from these two. So in order to use the correlation matrix, we would be using our syntax as df.corr brackets. So here this is our correlation matrix. Now in order to plot our correlation matrix, we would be using again C-bond from our libraries, and we would be using a heat map. As you can see, now using C-bond, we have plotted the heat map for our correlation matrix. Next up is the label encoder. The label encoder is usually helps us in dealing with data sets which contain multiple labels in one or more than one columns. These tables can be in the form of words or numbers. Label encoding refers to converting the labels into numeric form so as to convert it into machine readable form. So what we are going to do is, from sklearn.preprocessing, we are going to import our label encoder, and then we are going to define it as LE. In the df species, we are going to do le.fit underscore transform df species. Sorry. So here you can see earlier we had species where we had species, it was written as the name of the species, like Iris setosa here. But after we have used the label encoder, it has helped us to convert the label into the numeric form so that it is more easier for the machine to learn this data and hence move forward. So as you can see, the species has been turned into the zero. Next up is the model training. To train the data set and then test the data to validate. So we would be importing our model train test split, and we would need to split our data into training and testing. Here, as you can see, we have used 70% of our data in order to train our dataset and then 30% in order to test it. Here our variables x and y have been set as df.drop brackets columns equals species, while y is equal to df species. Next is our line, which would help us to validate our train and test split. You can also see that our test size has been set to 0.30 as we have used the test to be 30% of our data. Next, we would be importing a basic classification model, that is logistic regression. So importing modules is very easy from sklearn. As you can see, we have imported logistic regression from the sklearn.linear model and then defined it as model. Next up is that we would be training this model in order to fit from a test and train split. After doing that, we can print the metric to get the performance. In order to do that, we would be using the simple syntax of print accuracy. Then the model score x test y test would be multiplied by 100 in order to give us an output of percentage. As you can see, we have got a percentage of 95.5%. Next up, we are using the KNN algorithm, which is also known as k nearest neighbors. Similarly, as we did earlier in the logistic regression algorithm, we would be similarly doing it here. In the KNN, we would be importing the kneighbors classifier from the sklearn.neighbors and then define the model as kneighbors classifier. Again, we would train and test the data, and after that we would print the metric to get performance. As you can see, this has given us the accuracy of 100%, which tells us that kneighbors classifier is the best algorithm for an iris data set. Now let's use a module which is trained with default parameters. For example, the decision tree. This is a very high level module, and this is supposed to work better for complicated data sets rather than a simple and simplified dataset like iris dataset. Let's go and load this from our sklearn.tree, then test this, and at last print the accuracy. As you can see, the accuracy is not the best when it comes to the decision tree, though it is a high level module. But as I had said earlier, these high level modules tend to work better with complicated datasets. That's why we have a change of accuracy when we use a simplified data algorithm like KNN rather than decision tree classifier. So we basically need to check the accuracies as we go forward and use different algorithms to get the best accuracy possible. So this was the basic analysis for iris dataset, where we started by pre-processing the data, use the EDA, get our plots done, and after having a view of our data in the plots, we used correlation matrix and then also label encoders to gain more insightful knowledge and help us train better. Then finally we used the model training algorithms like logistic regression, KNN, and decision tree, where KNN gave us 100% accuracy. So that's it for today's video, and in the future projects we will be using more concepts, and all the required links for this video will be in the description. Thank you.